Okay, we're continuing from the last video. We are finding, in part B, we were using Descartes' rule of sign to find the quantity of positive and negative real zeros and imaginary zeros, the possible scenario, the possible quantities. And we're taking all the information from the previous video and putting it together here with our table. So this is part B, but it's a continuation of part B. So you can go back, see that video, and see where this all came from. We're going to make a table, and our table is going to have 3 rows, and it's going to have 4 columns. The first column is the positive real roots. The next column will be the negative real roots. The next will be the imaginary roots. And finally, that will all be added together to equal the total roots, the total complex roots. Okay, here are our columns, and now our rows. The first situation we found in the previous video was that there could be either 4 positive real roots, or there could be 2 positive real roots, or 0 positive real roots. As far as negative real roots, there could only be 0. So in each case, I'm going to add 0 negative real roots. And then I know that when I add the imaginary roots to each of these, it has to total the degree of the polynomial, and you see the degree of the polynomial is 4. So each of these rows must equal 4. That's going to tell me what to put in here for the quantity of imaginary roots. So for the first row, 4 positive plus 0 negative real roots plus something has to equal a total of 4. That means there's going to be 0 imaginary roots in this case. In the next row, 2 positive, no negative, plus something has to total 4. So that means 2 imaginary roots. And the last row, we have 0 positive, 0 imaginary, and it has to equal 4. So that requires 4 imaginary roots. So we figured out what to put in the little boxes by looking at what we had found in the previous videos for the quantity of positive and negative real roots. Now, what I want you to note is that these are possible scenarios. So these are the possible quantity of real and imaginary roots. And if we take the problem all the way to the end, what our answer is will be one of those 3 rows. And we'll check back to see what that is. Now let's go on to part C. Here we're supposed to use the theorem on bounds to develop an integral bound on the roots. What number does the root have to be, greater than or less than or whatever? So first of all, I want you to notice that back in part B, we found that there were no negative real roots. If there's no negative real roots, it's impossible to find an integral lower bound. So there are no lower bounds. But remember, lower bounds are negative numbers, right? So don't even bother looking for this guy. He doesn't exist. Let's look for the upper bound. We're going to do this by taking the coefficients of the polynomial and synthetically dividing by integers starting with r equal 1. So that's our first, r equal 1. And so we're going to put a 1 on the outside and synthetically divide. Let's write our coefficients. Coefficients will be 1, then negative 4, then positive 7, then negative 16, and then positive 12. Leave some space, make a line, bring down the first number, 1, multiply, 1 times 1 is 1, add, you get negative 3. Multiply 1 times negative 3 is negative 3, add, you get positive 4. Okay, we can stop right here. We're looking for an upper bound. What type of scenario are we supposed to be having on the bottom? We're supposed to have all non-negative. But just for the heck of it, I'm going to go ahead and take this all the way through. I could have stopped as soon as I got that negative and say, hey, this is not going to give me an upper bound, but what the heck? Let's just finish. 1 times 4 is 4. Because it is kind of fast, let's just do it. So that gives us negative 12 when we add. 1 times negative 12 is negative 12. 0, oh my goodness, happy day, happy day. I put a happy face on here. Yay, party time. What does this mean? Well, we certainly didn't find our upper bound, because to have an upper bound, we'd have to have all non-negative numbers on the bottom of our synthetic division. But what we did find is that r equals 1 is a root. We found one of our roots, and I wasn't even trying that hard. I was looking for an upper bound. Okay, but not an upper bound. But not upper bound, which means we have to continue our search for the upper bound. So next, let's let r equal 2, the next whole number. moving larger and larger each time. So here's our 2 that we're checking to see if it's a root, and we're synthetically dividing into the same coefficients. 7, negative 16, 12. Make a line after some space, bring down the number. 1 times 2 is 2. Add, you get negative 2. Multiply, you get negative 4. Add, you get positive. Okay, see, again, we're alternating. We got a sign change, and that's no good for the upper bound. But since I'm so far into it, again, I'm going to say, well, what the heck? Let's just go ahead and finish it up. 2 times 3 is 6. Add, I get a negative 10. And then 2 times negative 10 is negative 20. Add, I get a negative 8. Now, that told me nothing. That told me absolutely nothing. But, all right, it was a good exercise. But it's certainly not an upper bound, because I'd have to have a positive testing a positive r equals positive 2, and get all non-negative on the bottom. It didn't even give me a root like the last one was. It gave me a root for free, but not this one. Okay, let us continue now with r equal 3 and see what happens here. Maybe we'll get lucky. 3 synthetically divided into 1, negative 4, 7, negative 16, 12. Make a space, a line, bring down the 1, multiply, you get 3. Add, you get negative 1. Multiply, you get negative 3. Add, you get positive 4. Multiply, you get a negative 12. Wait a minute, is it negative? 3 times positive 4 is a positive 12. Add, you get a negative 4. See, again, look, I'm doing this so quickly I don't even worry about the fact that I'm not getting all non-negative on the bottom, which I want. I'm looking for an upper bound. But that's okay. I'll just go ahead and finish. 3 times negative 4 is good news. We did it again. Accidentally came across a root. Yes, sirree. Here we go. So we found a root. What does this 0 remainder at the end tell us? It tells us that the r we were testing equals 3 is unexpectedly a root. That is very good news. We have found 2 roots for this polynomial. But again, it is not an upper bound. So we haven't fulfilled that, but my goodness, we found 2 roots. Okay, don't give up. Let's try again. R equals 4. All right, we're going to synthetically divide the same coefficients, 1, negative 4, 7, negative 16, and 12. Synthetically divide by 4. Make a space, bring down the first number. 1 times 4 is 4. Add, you get 0. And that can be any sign we want. I choose to make it positive because I'm hoping to get all positive on the bottom. 4 times 0 is 0. Add, you get 7. Okay, it's looking good. We've got positive again. Multiply. 4 times 7 is 28. 28 minus 16 is positive 12. Oh, this looks really good. If we can just get one more positive number, then we have our upper bound, our integer upper bound. 4 times 12 is 48. 48 plus 12 is 60, positive 60. That's excellent. So we have all positive on the bottom, and that implies that r equal 4 is our upper bound. Now, there's more than one upper bound. There always is more, but this is our smallest upper bound. Okay, now we didn't have a lower bound, but we did find an upper bound, and we accidentally found two roots. So conclusion, we got a nice conclusion going here, more than we expected, actually. We were not able to find a lower bound because there is no lower bound, but we did find that x or r equal 1 and equal 3, each of those individually are roots or zeros of the poly, and we found that there is no root that exists for this polynomial that is larger than our upper bound, which is equal to 4. So we got lots of information there. That was a good thing. Okay.